today I want to talk about PWM. Now, in the previous tutorial we have looked at timers and how they work, and PWM is really just a little addition to a standard timer. So what we have here is we've still got our oscillator block. So we've got the internal instruction clock, which is the oscillator clock divided by 4, that drives the prescaler, which then drives the timer. So the timer register gets increased every clock cycle depending on the prescaler, as we have talked about previously. Now then we have another module, another peripheral in the microcontroller called the capture compare module. Now what that does is it compares its own compare register to the timer value, and as soon as these two match, it actually sets a GPIO pin low or high depending on if it's active high or active low PWM. Now let's have a quick look at what PWM actually is. So I've got a diagram here. We see this is the voltage on the pin and this is time. So we can see in the on time our signal is high because we have got an active high PWM. If this was an active low PWM, the signal would be low here. And then as soon as the timer count actually matches the CCP register, the pin gets toggled low. And then it's low for the off time of our PWM cycle. And then as soon as the timer overflows, we get a rising edge again, so the pin is set high again. And we can control the whole or the complete time of one of these sweeps with the PR2 register, which is the timer period register. The PR2 register is an 8-bit register because in PIC microcontrollers for PWM generation you can only use 8-bit timers. So then to calculate the PR2 register for a specific frequency or a specific period, we have to take the oscillator clock, divide that by 4, because remember the whole system is clocked by the oscillator clock divided by 4, times the prescaler, which can be a value of 1, 4, or 16, times the frequency of our PWM signal, so the inverse of the period of this signal. And then minus 1, because as you can see here, the counter actually starts at 0, and then it counts 1, 2, 3, 4, 5, 6, 7, and there we've got a match with the CCP register, and then it sets it low, and then it counts, it goes on, 8, 9, and well, you would imagine this to be the rising edge, because you set your PR2 register up like that you want 10 counts to occur. Remember, 0 is also a count here, so there are actually 10 counts from 0 to 9. And but actually this edge occurs when the timer overflows. So when the period register is actually increased one more and then the timer is reset. So we have to set PR2 equal to this term minus 1 so that we get our correct frequency. Otherwise we would get a frequency that is a little bit too fast as what we've calculated or what we would actually expect it to be. And then there's another thing called duty cycle, which actually is just the relation of the on time to the total time, so to the total period of the PWM cycle. So it's actually T on over T on plus T off, which also is equal to CCP R, which is a CCP register, over PR2 plus 1, because T off is as long as CCP and the timer don't match, and then the whole period is until PR2, until the period register actually gets increased so that it overflows, so it's PR2 plus 1. So let's have a look at the code, and then I'll show you the example application. So let's have a look at the demo application. we're using the PIC18F14K22, the same we've been using in the last video. And the only thing I changed in the configuration bits is that we're using the internal RC oscillator instead of an external oscillator. And that the frequency of the internal RC is by default 1 megahertz. And we don't change that, so we just leave it at the default of 1 megahertz. Then here in the main loop, we start out by setting our PWM output pin, which is RC5 in our case, to be an output, so we enable the output driver. Then we configure the CCP1 module with the CCP1M bits, so mode bits, and we set it to PWM mode, because remember the CCP actually has multiple modes, capture, compare, and PWM, and so we have to tell it that it is supposed to be a PWM generator, and we also want P1A, which is the channel we're using, to be active high, and that's what we've looked at before on the paper. Then we set CCPR1, the compare register, to be 77, which is half of our maximum period value here in the PR2 register of 155. And we calculated that by saying we have 1 megahertz of clock frequency. We divide that by 4 times the prescaler, which is 16 in our case, times the output frequency that we want, which is 1 kilohertz, and we subtract 1 because remember the output is actually set high on PR2 plus 1, so we have to subtract 1, and that gives us a value of 155 for the period register. Then we set the clock prescaler of the timer 2 to be 16, which is this value right here. And then we enable timer 2, so it starts counting up, and the CCP compares the timer register to the CCP register, and does what we've talked about before. And in the while loop, or in our main application, the only thing we're doing is we're counting up from 0 to 155, which is our maximum period, and the count value actually is written to the CCPR1 register, which is the compare register, and then we delay the loop by 6 milliseconds each step, so each step is valid for 6 milliseconds, so that we count from 0 to 100% duty cycle in 1 second. So I'm going to load this code onto the chip and we'll have a look at what it does. So this is the example application. We can see our PIC microcontroller right here, and we've got it connected to a resistor, or we've got the PWM pin connected to a resistor, and the resistor is connected to the anode of an LED here, and the LED's cathode is connected to ground. And as you can see, as we've seen in the example code, the LED actually fades up, and if we were to make the PWM much slower, then we could actually see that the LED is not actually getting brighter, but it's just switched on and off all the time. And by varying the duty cycle, varying the time the LED is switched on, we can actually vary how bright it is. It's called persistence of vision, and it's basically because our eye cannot determine the fast on and off switching, because it's so fast that, well, it looks like it's constantly on and it's just fading from 0 to, well, full brightness. So anyway, thanks for watching, and if you like this video, then give it a thumbs up and subscribe to my channel. Thank you.